Welcome to today's paper reading. Today's paper is titled, TexDreamer, Towards Zero-Shot High-Fidelity 3D Human Texture Generation. This paper was published on AR14 by Yufei Liu and colleagues from Shanghai University and Tencent U2 Laboratory. The abstract introduces TexDreamer, the first zero-shot multimodal model designed for high-fidelity 3D human texture generation. This model employs an efficient texture adaptation fine-tuning strategy to adapt large text-to-image models to a semantic UV structure while maintaining their original generalization capabilities. A novel feature translator module enables the model to generate high-quality 3D human textures from either text or images in a matter of seconds. Additionally, the abstract mentions the Atlas dataset, which is the largest high-resolution 3D human texture dataset, containing 50,000 high-fidelity textures with associated text descriptions. 3D human texture is crucial for creating visually appealing 3D models. UV mapping ensures accurate texturing by minimizing distortions. However, obtaining high-quality textures is often a time-consuming and costly process involving 3D scanners and skilled artists. TexDreamer addresses these challenges by being the first zero-shot multimodal method for high-fidelity human texture generation, capable of handling both text and image inputs. Figure 1 provides an overview of the Atlas dataset on the left, which is the largest high-resolution 3D human texture dataset to date, featuring 1024 by 1024 resolution textures paired with textual descriptions. This dataset includes both real and fictional identities. On the right, the figure illustrates the basic structure of TexDreamer, the first zero-shot high-fidelity human texture generation method capable of handling both text and image inputs. This method is designed to generate high-quality 3D human textures efficiently, addressing the challenges in the field of 3D human texture creation. The Atlas dataset is compared with existing human datasets in terms of 3D shape precision, UV textures availability, and texture generation methods. 3D scans offer the highest precision but are challenging to acquire due to the complexity and time required. Only a few datasets include UV textures, with Surreal providing 921 UV textures, though privacy policies limit their diversity. Recent advancements in neural networks and text-to-3D generation have shown potential in creating 3D models from single images and text descriptions, respectively. Image-to-image generation methods, often using GNs, are also employed to create UV textures. Table 1 provides a detailed comparison of our Atlas dataset with existing human datasets in terms of 3D shape, UV textures, texture resolution, and text description. Key points include the high number of UV textures in Atlas, 50K, the significant number in Thuman 2.0, 526 * operator, and the relatively lower count in Surreal, 921. The table highlights the unique features and resolutions of each dataset, emphasizing the superiority of Atlas in terms of texture quality and diversity. Figure 2 illustrates the pipeline for generating synthetic data. On the left, the process of sample texture acquisition is shown. Initially, a differentiable render is employed to optimize UV maps from multiple views of images. These UV maps are then further refined using projection painting, a technique commonly used in CGI production. The acquired sample textures, along with corresponding prompts, are utilized to train the T2 UV module in TexDreamer. On the right, the process of diverse textured human synthesis is depicted. Leveraging ChatGPT, the T2 UV module generates 50,000 human textures. These textures are applied to human images that are rendered with an animation sequence, background image, HDR lighting, and a perspective camera. Orange stars in the figure indicate data included in our Atlas dataset. The Atlas dataset is designed to provide large-scale human textures with optimized UV mappings, which are essential for training TexDreamer. The data generation strategy involves two main processes: sample texture acquisition and diverse textured human synthesis. The visual pipeline includes UV projection to optimize coarse UV maps from multi-view images, followed by project painting for refinement. Composite rendering enhances authenticity with HDR lighting and PBR shaders, while incorporating backgrounds increases realism. This dataset supports the training of TexDreamer by providing diverse and high-quality human texture data. TexDreamer is the first zero-shot multimodal high-fidelity 3D human texture generation method. It employs a two-step training strategy involving the text-to-UV, T2UV, and image-to-UV, I2UV modules. The T2UV module uses efficient texture adaptation fine-tuning with LoRa to generate textures from text. The I2UV module, on the other hand, utilizes a novel feature translator to map input image features to the conditional text feature space of T2UV, enabling the generation of UV textures from 2D images. Figure 3 illustrates the structure of TexDreamer, detailing its two-stage training process. The first stage, T2UV, involves optimizing the text encoder and UNet using LDM denoise loss L1. This stage is depicted in green. The second stage, I2UV, is shown in blue and involves the feature translator IT mapping input image features encoded by I-Enc to a conditional feature Phi2T. The I2UV stage is trained by optimizing T-Enc and I-Enc with L2. This dual-stage approach is crucial for the efficient and effective generation of high-fidelity 3D human textures. Figure 4 illustrates the contrast in attention maps between the original Stable Diffusion (SD) model and the TexDreamer T2UV model. The original SD model exhibits a random response area when processing text prompts, indicating a lack of consistent mapping. In stark contrast, the TexDreamer T2UV model consistently maps the text prompts to a learned UV structure. This consistent mapping is a significant improvement, as it demonstrates the model's ability to generate textures with a semantic layout, which is crucial for applications involving human textures with various identities and clothing. This learned structural information highlights TexDreamer's potential in generating large-scale human textures with high text-image consistency. For training T2UV, the authors utilized two key models, Stable Diffusion 2-1 and ClipFit Large Patch 14-336. The rank and alpha values for the UNet and text encoder were set to 128 and 16, respectively. Each training session used a batch size of 8, with a total of 2,000 training steps. The optimizer chosen was AdamW, with a learning rate of 0.0001 and a constant scheduler that included 100 warm-up steps. During inference, the weight of T2UV was set to 1.0, and the process was completed in 32 steps, all conducted on a single NVIDIA A100 GPU. Figure 5 presents a qualitative comparison of texture generation from text, featuring TexDreamer alongside state-of-the-art methods such as text-to-text, texture, latent paint, and Fantasia 3D. The results demonstrate that TexDreamer achieves the finest facial details and the highest overall quality in texture generation. This comparison highlights the superior performance of TexDreamer in generating detailed and high-quality textures from textual descriptions. For a more detailed view, please zoom in on the figure. Figure 6 presents a qualitative comparison of TexDreamer's texture generation capabilities with state-of-the-art methods Avatar Clip and Avatar Craft. On the left, our method demonstrates more realistic head avatars, highlighting superior texture realism in facial features and colors. The right side showcases TexDreamer's ability to edit texture details using text, such as altering clothing styles, colors, and accessories, thereby offering a more flexible and precise tool for character design in creative industries. Figure 7 presents a qualitative comparison of UV generation from images, contrasting our method with advanced techniques TextFormer and SMP LaTeX. The comparison is conducted on two datasets, our Atlas dataset, shown on the left, and the Market 1501 dataset on the right. The figure encourages viewers to zoom in to closely examine the texture completeness and quality, highlighting the superior performance of our method in these aspects. Table 2 provides a quantitative comparison of various methods for generating human textures from text descriptions. The table highlights the efficiency and performance of TexDreamer T2UV in terms of GPU usage and time consumption, showing it to be the most efficient method with 5.71 GPU GB and 0.17 minutes. It also compares the clip scores of different methods, where TexDreamer T2UV achieves a score of 31.297, while Avatar Craft's score is not reported due to high resource consumption. The table further contrasts TexDreamer T2UV with other methods such as Text2Text, Texture, Latent Paint, Fantasia 3D, and SMP-LaTeX, providing a comprehensive view of its performance in the context of human texture generation. Table 3 presents the results of a user study on texture generation from text. The study evaluates the image quality and text consistency of various methods. TexDreamer, our proposed method, achieves the highest scores in both image quality, 4.244, and text consistency, 4.019, outperforming other methods such as Text2Text, Texture, Latent Paint, Fantasia 3D, and Avatar Clip. This indicates that TexDreamer not only generates textures that are visually appealing but also maintains a high level of consistency with the input text descriptions. Table 4 presents a quantitative comparison and ablation study of TexDreamer I2UV. The table highlights the mean squared error, MSE, and clip score for different methods, including TextFormer and SMP-LaTeX, as well as two versions of ours I2UV, one with a fixed image encoder, fixed I-Inc, and one with the full training process. The results show that the full version of ours I2UV achieves the lowest MSE of 0.0442 and the highest clip score of 27.334, indicating superior performance compared to other methods. The ablation study with the fixed image encoder demonstrates a higher MSE of 0.0632, illustrating the importance of training the image encoder in I2UV. Table 5 presents an ablation study of TexDreamer T2UV, focusing on the settings that achieve the highest text consistency. The table compares different configurations of unetter, unet T-anchor, and T-anc, which are parameters related to the unet and text encoder. The results show that our setting achieves the highest clip score, indicating superior text consistency. This study underscores the importance of these parameters in optimizing the texturing process for 3D human models. TexDreamer's capabilities extend to editing 3D human appearances, allowing for precise alterations in clothing styles and accessories. This flexibility is particularly useful in character design for film and game industries. Additionally, TexDreamer can texture dressed avatars, integrating with complex human meshes to produce authentic characters. This is achieved by leveraging advanced text-to-3D avatar generation methods like Tada. The method also facilitates a fast virtual try-on, enabling the creation of personalized characters efficiently, a task that would traditionally be laborious using 3D modeling techniques. Figure 8 demonstrates the application of TexDreamer in texturing dressed avatars. The human textures generated by TexDreamer can be seamlessly applied to complex dressed meshes created through text-to-3D methods. Specifically, the figure showcases examples where Tada 29 is used to generate the dressed meshes, while TexDreamer provides the synthetic UV textures. This integration not only preserves the identity of the avatars but also facilitates a fast virtual try-on experience, enhancing the flexibility and realism of 3D human avatar creation. The TexDreamer model represents the first zero-shot multimodal approach for high-fidelity 3D human texture generation. It leverages efficient texture adaptation, fine-tuning, and introduces a novel feature translator to accurately generate textures from text or images. Additionally, the Atlas dataset, which is the most extensive high-resolution 3D human texture dataset to date, provides a uniform and semantic UV layout, addressing the lack of high-quality human UV data. Despite these advancements, the model has limitations, such as not being based on dense pose segmentation for real-life applications, and raises ethical and privacy concerns due to its potential use in creating deepfakes. Thank you for watching.